Hello, chemistry students. Dr. Tullis here. This section is about electronegativity, using it to determine the polarity of bonds, and using electronegativity and formal charge to predict the charge distribution in molecules and polyatomic ions. Here is our electronegativity cheat sheet chart that we are going to need to be using to help us when we are looking at bond polarity. So far, we've talked a lot about covalent bonding. We've drawn their Lewis structures, we've predicted their molecular shapes, but pure covalent bonding is when atoms share an electron pair equally. And that only occurs when two identical atoms are bonded. All homonuclear diatomic molecules are nonpolar. When two dissimilar atoms form a covalent bond, the electron pair will be unequally shared. The result is a polar covalent bond, a bond in which the two atoms have partial electrostatic charges. How do we tell this? Well, we use electronegativity values. For example, iodine, I2, it's in Brinkelhoff, one of the 7 diatomic molecules. If I look back at my electronegativity sheet and look at iodine, it has a value of 2.7. So if I have two iodines bonded together, like right here, I would do 2.7 minus 2.7 to get this 0 difference of electronegativity. And that tells me that they are sharing their electrons equally. It's a homonuclear diatomic molecule and it is nonpolar. A difference of 0 is nonpolar. Now we actually stretch that difference to 0.4 and call it molecules that are 0.4 and less nonpolar, but this is a pure nonpolar, all homonuclear diatomic molecules. Bonds are polar because not all atoms hold on to their valence electrons with the same force or take on additional electrons with equal ease. For example, if I have HI and I look at H's value is 2.2 and I's value is 2.7. To find the difference, we just subtract. 2.7 minus 2.2 is 0.5. I'll show you the ranges in just a minute, but I told you 0.4 and less was a nonpolar. So if it's 0.5 and up, we call that polar. That means that the atom with the greater electronegativity value is going to pull those electrons closer to it, giving it a slightly negative charge. If it's pulling hydrogen's 1 electron, instead of hydrogen's 1 electron and iodine's 1 electron sharing it peacefully, iodine is actually going to pull that electron, let's say maybe right here, when iodine's electron is right there. So let's say it's more like this, an unequal tug of war. So I have more electrons closer to iodine. It's not a negative charge, it's just a partial, slight negative charge. In hydrogen, it's almost like it gave away its electron. It didn't. It's just losing that tug of war. So it's a slightly positive charge. So it has poles, making it polar. And we show that by denoting the slight positive, slight negative, and pointing an arrow towards the more negative atom. This slide pretty much sums up everything I just said. If a bond pair is not equally shared between atoms, the bonding electrons are on average nearer to one of the atoms. It's winning the tug of war. The atom toward which the pair is displaced has a larger share of the electron pair, so it has a partial negative charge. At the same time, the atom at the other end of the bond is depleted in electrons and has a partial positive charge. The bond between the two atoms is polar. That is, it has a positive end and a negative end. And it actually isn't a complete positive. It's a slightly positive end and a slightly negative end. The electronegativity of an atom is defined as a measure of the ability of an atom in a molecule to attract electrons to itself. Here is our electronegativity difference range. We say from 0 to 0.4 are nonpolar, especially diatomic molecules. We have our polar covalent range, which is between 0.4 and 1.6. And again, we denote those with our slightly positive, slightly negative symbols. And then we have our ionic. Now, ionic bonds are just very, very polar bonds. They're actually giving away and taking electrons to become charged. Hopefully it's starting to sink in that electrons may not be shared equally. And we tell this based off of the electronegativity difference between two elements that are forming that bond. And to see if they are polar covalent, that difference would have a value between 0.4 and 1.6. If the difference is 0 to 0.4, we call it nonpolar covalent. If it's greater than 1.6, it's ionic. Electronegativity, when we look at the chart, electronegativity increases as you go up a group, and it increases as we go to the right. Fluorine has the greatest value of electronegativity. And we'll talk more about this in a minute, but if we're looking at a molecule and there's no polar bonds in that molecule, for example, if I have methane, CH4, and I look at the values, because there are 4 CH bonds in this molecule. Let's look at those values. Carbon has a value of 2.5 and hydrogen is 2.2. So 2.5 minus 2.2 gives me a value of 0.3, which is a nonpolar bond. If I have 4 nonpolar bonds, each one of these bonds would be nonpolar, then I have a nonpolar molecule. If I have a molecule with 1 polar bond, it's a polar molecule. If I have an individual bond where the dipoles do not cancel, the molecule is polar. And I'll show some examples of these in a minute. If I have an individual bond where the dipoles cancel, that molecule is nonpolar. And if there are any lone pairs on the central atom, we have a polar molecule. When I'm mixing two things together, let's say 2 solutions, I have a polar solution and I have a polar solute that I'm putting in, they will dissolve. Likes dissolve likes. Same with if I have a nonpolar compound dissolving in a nonpolar solution, they will dissolve. Likes dissolve likes. That's why oil and water do not mix. Water is polar. Oil is nonpolar. They don't mix. Ethanol and water do mix because they're both polar. As the difference in electronegativity increases, so does the ionic character of the bond. Again, here I'm starting with totally covalent, again, totally nonpolar covalent, because my difference in electronegativity is 0. Here I have HF, and it's showing that the electrons are really getting pulled closer to fluorine, so it's slightly negative. The smaller value, in this case hydrogen, that's the smaller value, is always the slightly positive end. The larger value, the 4.0, comes from fluorine. That's the slightly negative end. And you can see here as I go to the right, lithium fluoride, lithium becomes completely positive, not just slightly positive. Fluorine becomes negative, not just slightly negative, because it's ionic. That difference, if I took fluorine's 4.0 and subtracted lithium's 1.0, we get 3.0. And remember, ionic compounds start at about 1.6, anything greater than 1.6. So we are definitely looking at an ionic compound here. And again, ionic compounds are extremely polar molecules. Here's another example, HF. If I look at this bond, fluorine has a value of 4.0 and hydrogen has a value of 2.2. 4.0 is obviously the larger of the two, so it's the more negative end of that compound, making hydrogen the more positive end. This means that the electrons are skewed towards the fluorine atom, and those electrons shift towards the fluorine atom, and that polarizes the molecule. Let's look at 3 different bonds. The greater the difference in electronegativity, the more polar the covalent bond is. We're going to look at HF, CF, and OF. We're just going to subtract those values. 4.0 minus 2.0 to give us 1.8. C and F, 4.0 minus 2.5, and 4.0 minus 3.5. And then we just put them in order of greatest to least. HF is going to be my most polar because it's the greatest difference, and then CF, and then OF. Using your electronegativity chart, can you put these in order of increasing electronegativity? Hopefully you've got the third option because fluorine is the greatest. Here's another similar problem. Can you put them in order of increasing electronegativity? Hopefully you got number 2. Which one of these pairs would have the greatest bond polarity? And if you subtracted them, you should get KF. And which one of these bonds is least polar? If you subtract it, you should get CB. For each of these bond pairs, decide which bond is more polar and indicate the negative and positive poles. I looked up their values on the electronegativity chart. Both BF and BCl are polar. I got a difference of 2.0 and 1.2, but BF is more polar because it has a greater value, and the slightly negative end is going to be the fluorine end. So I would show that with an arrow pointing towards fluorine, and my F would be my slightly negative end, and my B would be my slightly positive end. For SiO and PP, PP is nonpolar. It's pure nonpolar. It's going to have electronegativity difference of 0. SiO has a difference of 1.6, which is highly polar. The slightly negative end is going to be on the oxygen end, and my slightly positive end will be on the silicon end. Here are 3 more just like those last ones. Pause the video here. Looking at A, the hydrogen atom is the positive pole in each case. HF is more polar than HI, who have a much greater electronegativity difference. In BC and BF, the boron atom is the positive pole in both cases, and BF, with a difference of 2.0, is more polar than BC, which has a difference of 0.5. And for these two, letter C, CSI is more polar than CS. In CSI, C is the negative pole because it's the greater electronegativities. So I would be pointing towards the carbon end, which would be slightly negative, and Si would be slightly positive.